Hello, and welcome to the fourth video of the M2 chapter Variable Acceleration, an exam question on the screen to get us going. A particle p moves on the x-axis. The acceleration of p at times t is this, measured in the direction of x increasing. The velocity at time t is v. Given that v is 6 when t equals 0, find this and this. Very quickly here we've got a boundary condition, and here is the acceleration formula. So to find v in terms of t for part A, we need to integrate the acceleration, which gives us the integral of 4t minus 8 with respect to t, which is 2t squared minus 8t plus c. Now we can use our boundary condition that when v is 6, t is 0. Put that in. V is 6 when t is 0. And we find that the constant is 6. So our final function for v in terms of t is 2t squared minus 8t plus 6. Part B, we need to find the distance between the 2 points where p is instantaneously at rest. So for the distance, we need to integrate the velocity function with respect to time. But we need to first find the limits. What time points do we need to find this between? It's the 2 time points where p is instantaneously at rest. What that means is just a fancy way of saying when v equals 0. So first I'm going to put v equals 0 in here, solve to find the 2 times when p is instantaneously at rest, and then integrate between those 2 times. Before I do the integration, I'll just do a very quick check that between these 2 times that I find, the v function does not cross over the t-axis. So we don't have to worry about accidentally adding in a negative distance, because of course we can't have negative distance. So first, v is equal to 0. I can factorize this to give 2t t with a minus 3 here and a minus 2 here. That gives me t is equal to 1 and t is equal to 3 as the 2 time points at which p is instantaneously at rest. So now I can go ahead and put them here from 1 to 3, but like I said, let's just check. It's a bit easier on this one than with some of our examples because this is a quadratic. So we know that if this is a 1 and this is a 3, it's going to go like this, and of course those 2 points where it crosses the axis on a quadratic are the only 2 points. So we know for sure it won't cross in between these 2 points. So integrating from t equals 1 to 3 all in one go is no problem. So let's go ahead and do that. The integral of the v function, 2t squared minus 8t plus 6, from 1 to 3, 2/3 t cubed minus 4t squared plus 6t. We don't need a constant because we're putting in limits 1 to 3. And then the calculation. 2/3 3 cubed minus 4 3 squared plus 6 times 3. All of that minus 2/3 minus 4 plus 6 when t is equal to 1. Putting that on my calculator gives me 0 minus 8 over 3. Of course, minus 8 over 3 is our displacement, but that should not be the distance, because distance can't be negative. So although this is s, now I'm going to write the distance equals 8 over 3 meters. In this video, we're not going to do very much different to what we did in the previous two, except that we're going to be using that calculus to solve problems involving vectors. We can apply differentiation and integration to vector quantities by treating the I and j components separately. This is one of the 2 key points here. Much of this work is the same, but you must do integration or differentiation on the I and j components separately. They're independent. The second thing is that when you integrate to give a constant of integration, that too must be in a vector form with I and j components. Either you can write that separately as an ai plus bj constant, or you can put a constant of integration inside the I component and another one inside the j component. Effectively the same thing. Sometimes you will be required to find it using boundary conditions in the usual way, but if not, make sure that there's a constant in each of those 2 components. That's all the notes in terms of the concept. There's not a lot new in this video, But there is something about notation that we should sneak in here as well. In mechanics, we often use differentiation with respect to time. That's what we're doing in most of these videos in this chapter. And it has a particular notation to make it quicker to write. It's called the dot notation. If you see x with a dot on top, what that means is dx by dt. And you can put 2 or 3 dots, and that just indicates the second or third derivative. You can do this with vectors as well. So v as a vector here with a dot is still a derivative with respect to time. And of course you can do it with y's or anything else that you need to do a differentiation with respect to time. The key thing to remember here is that you only do this with differentiation with respect to time. Don't use this notation for differentiation with respect to any other variables, only time. And you don't have to use it, but it's worth knowing just in case you come across it and you need to know how to interpret what you're seeing. The following examples are all of the examples in the textbook for the next 2 sections, because differentiation and integration are put into one video, because we've done all the concepts in the previous 2 videos. This is just applying it to vectors. So there's quite a few. First one here. Particle p of mass this is acted on by a single force this, relative to a fixed origin O. The position vector at time t seconds is r, where r is this. See the I and the j components here. T is greater than or equal to 0, find these things. So we need to find the speed of p when t equals 4. So straight away we're seeing the difference between vectors and scalars here. We've got the position vector, and from this we can differentiate to get the velocity vector, but that is different to the speed. Remember, speed is a scalar, and to get that from an I and j component velocity, we'll need to apply Pythagoras. But I'm getting ahead of myself. First, we need to find the velocity function, where v as a vector is equal to the derivative of the vector r with respect to t, or r dot if you like that notation. So applying what I said in the notes, we need to do this independently, i's and then j's. 2t cubed becomes 6t squared for the I component, and then we've got minus 25t to the minus 3 over 2 for the j component. When t is equal to 4, we put that into both components. V is equal to 6 times 4 squared, 96i minus 25 over 8j. Now for the speed, this is where we need to do our Pythagorean approach. This squared plus this squared square rooted gives us the magnitude of velocity, which is what the speed is. And you could argue that I should put negative 25 over 8 here, but because we're going to square it anyway, that doesn't really matter. And that gives us the answer 96.0508 dot dot dot. So I'm going to write 96.1 meters per second to 3 significant figures. And that is the speed of p when t equals 4. Part B needs the acceleration of p as a vector when t equals 2. If we want the acceleration, we need to differentiate the velocity. So we're differentiating this again. For part B, acceleration as a vector is equal to the velocity as a vector, differentiated with respect to time, or v dot, and that is equal to 12ti plus 75 over 2t to the minus 5 over 2j. That's the acceleration. When t is equal to 2, we put that in there and we get a is equal to 24i plus, in third form, 75 root 2 over 16j, or 6.63 to 3 significant figures in decimal form. Part C asks us to find f when t equals 2. F here you can see is in bold, so I'm going to assume they want it in vector form like this as well. And to find the force, we just do F is equal to mass times acceleration. We have the acceleration when t is equal to 2, so I just times this by the mass, 0.8. Which gives me 96 over 5i plus 15 root 2 over 4j in ij notation. Next example. A particle p is moving in a plane. At time t seconds, its velocity as a vector is v, given by this. When t is equal to 0, the position vector of p with respect to a fixed origin is this. Find the position vector of p at time t seconds. So this second sentence in here, when t is equal to 0, the position vector of p is this. This is a boundary condition. And here, find the position vector of p at time t seconds. This wants us to find the function with the variable t. So we need to integrate this to get the position vector, and then use the boundary conditions to find the constant of integration. We need position vector r is equal to the integral of v with respect to t. So we've got the integral of 3t I plus a half t squared j with respect to t, and that gives us 3 over 2 t squared I plus 1 over 6 t cubed j plus pi plus qj, where p and q are my two constants of integration, one for each component. So this is the general solution. Now I put in my boundary condition. R is equal to 2i minus 3j when t is equal to 0. So when t is 0, this is a 0i plus a 0j plus pi plus qj. So quite easy here. We find that p is 2 and q is minus 3. So this is the constant here. Putting that in gives me the final position vector of 3 over 2 t squared I plus 1 over 6 t cubed j plus 2i minus 3j, and if you prefer you can leave it like that with the constants on the end, or you can group your i's and j's, which is my preference. So I'll rewrite that like this, plus 1 over 6 t cubed minus 3j. And there we go, the position vector of p at time t seconds. Next example. A particle p is moving in a plane so that at time t seconds its acceleration is this. When t equals 3, the velocity of p is 6i. There's a boundary condition. And the position vector of p is this, with respect to a fixed origin O. So here we have a second boundary condition, and this and means that this is true when t equals 3 as well. So t equals 3, and the velocity is this. T equals 3, and the position is this. Two boundary conditions in one sentence. Part A, find the angle between the direction of motion of p and I, the x-axis, the positive x-axis, when t is equal to 2. Okay, here we need to understand what it means by the direction of motion. Remember, the acceleration is describing the change in speed. The position vector is just describing where the particle is. It's the velocity that is describing how it moves from moment to moment. So we need to find the velocity as a vector, then we can find the direction of the velocity, which tells us the direction of motion. So first of all, using acceleration given in the question, 4i minus 2tj, we need to integrate this to get the velocity. And that gives us 4ti minus t squared j plus pi plus qj. That's the general solution. Using our first boundary condition, t equals 3, the velocity is 6i. So 6i, when t is equal to 3, that's 12i here, minus 9j plus pi plus qj. If we equate the I and j components, we get 6 is equal to 12 plus p for the I, so p is equal to minus 6, and 0 is equal to minus 9 plus q for the j, so q is equal to 9. Putting those back into the velocity function gives us the final velocity function in vector form as 4t minus 6I plus 9 minus t squared j. Now we need to look back at the question. We want the angle between this and the x-axis when t is equal to 2. So substituting t is equal to 2 into this gives us v is equal to 2i plus 5j. 2i plus 5j very roughly is this. So the angle between this velocity vector here in yellow and the x-axis, or the I direction, which is this one, is this angle here, theta. The tan of theta is equal to 5 over 2, so theta is equal to the inverse tan of 5 over 2, which is 68.2 degrees to 1 decimal place. Part B, the distance of P from the origin O when t is equal to 0. So to find the distance, that's the scalar version of the displacement, so we need to apply Pythagoras on the position vector. But we don't have the position vector yet, we've got the acceleration and the velocity. To find the position vector, we need to integrate this. So for part B, the position vector is equal to the integral of the velocity vector with respect to time. I won't write all of that out again. I'll just go ahead and write the answer using this here. And this time, instead of putting p and q at the end, I'll put them separately in their i's and j's all together. So for the I component, when we integrate this, we get 2t squared minus 6t plus, oh, I shouldn't really use p again. Let's say a I plus 9t minus a third t cubed plus b j. And that is the general solution for the position vector, but we have a boundary condition in the question for this as well. When t equals 3, the position vector is 20i plus 3j. So if we put that in, 20i plus 3j is equal to, for the I component, 18 minus 18 plus a, that's nice. And for the j component, 27 minus 9 plus b. Separating them off into I and j components, we get 20 on the left is equal to 18 minus 18, 0. So that's a is equal to 20. For the j components, 3 on the left is equal to 18 plus b on the right. So b is equal to minus 15. Our final position vector solution then is equal to 2t squared minus 6t plus 20i plus 9t minus t cubed over 3 minus 15j. And the question again is find the distance of P from O when t equals 0. So working with t equals 0, I then have to find the distance using Pythagoras. So first of all, the vector, when t is equal to 0, r is equal to 0 minus 0 plus 20, that's 20i, minus 15j. So the distance from the origin is just applying Pythagoras here. Distance is equal to 20 squared plus 15 or minus 15 squared square rooted, which gives us a surprisingly nice answer of 25. Looking back at the question very quickly, I can see that this is meters. So there's quite a lot involved in that example. On to the next. The velocity of a particle p at time t seconds is this. When t is equal to 0, the position vector is this with respect to a fixed origin O. Find the position vector of p after t seconds. So we're going to integrate this, then use the boundary conditions to find the position vector. We know that v is equal to 3t squared minus 8i plus 5j, and the position vector is the integral of that. So we've got t cubed minus 8t plus pi plus 5t plus qj. That's the general solution. the particular solution, we need to put in the boundary conditions. When t is 0, the position vector is 2i minus 4j. T is 0 gives us pi here, plus qj here, so p is just 2, and q is minus 4, which gives a final answer of t cubed minus 8t plus 2i plus 5t minus 4j. Now that's an easier question than the one before it, because this is not the full question. A second particle, q, moves with constant velocity, this. When t is equal to 0, the position vector of q is 2i meters with respect to a fixed origin. Prove that p and q collide. Now to prove that these collide, we need to show that at the same time they have the same position vector, i.e. they're in the same place at the same time. We need to do this for the I component and also the j component. So first we're going to need to find the position vector of q. We've been given the velocity, so we've got v is equal to 8i plus 4j, so the position vector is the integral of that, which is 8t plus pi plus 4t plus qj. And our boundary condition, when t is equal to 0, the position vector of q is 2i. So we've got 2i when t is 0, qj, so p is equal to 2 and q is equal to 0, which gives r as 8t plus 2i plus 4tj. From the previous screen, we had the particle p with the position vector t cubed minus 8t plus 2i plus 5t minus 4j. Now to show that these two collide, we need a time when they are both in the same place. So the I component here, when I put in a certain value of t, must be the same value as the I component here for that same t. And the j component here for that same t must match the j component here for that same t. In order to find what that t is, I need to make this equal to this, or this equal to this. Now obviously the j's are going to be easier in this case, so I'm going to take 4t is equal to 5t minus 4, which gives me t is equal to 4. That's the only solution where this j component and this j component are the same for a given time. It must happen at t equals 4. In order to prove that the particles collide, however, I also need to show that this is true for I, that both of these are the same value for that same time. So putting t is equal to 4 back into those equations, we get r is equal to 32 plus 2i plus 16j, which is 34i plus 16j for particle q. For particle p, we get r is equal to 64 minus 32 plus 2i plus 20 minus 4j. And that does indeed give us the same answers, 34i plus 16j. So because they have the same position vector at the same time, they're in the same place at the same time, that means that the two particles must collide. Recapping very quickly, to prove that two particles collide, you must have their position vectors, equate one of the components to get the time for which it is equal, and also use that same time in the other component to show that that too is equal. When you've shown they have the same position vector in both components for the same time, you have proven that the particles collide. I hope that's enough for you to have a go at some of the questions in exercise 2D for differentiating vectors, and in 2E for integrating them. And maybe I'll see you for the final video of the chapter, proving some of our constant acceleration formulae.